So, I am Dr. Shivanand Senakote, Department of Physics, Faculty of Mathematical and Physical Sciences. So, I am going to do lectures on special functions. For this, syllabus is Bessel functions and their generating functions, integral representation, and the recurrence relations for Bessel functions of first kind and orthogonality. Then, after Bessel functions, we go for Legendre functions, generating functions, recurrence relations and special properties, orthogonality, and various Legendre polynomial associated Legendre functions, recurrence relations and orthogonalities. Then we will discuss Hermite functions and Legendre functions, their generating functions, recurrence relations and orthogonality. First, we will discuss what is meant by a special function. A special function is a term loosely applied to additional functions that arise frequently in applications. Algebraic, trigonometric, exponential, and logarithmic functions are the elementary functions. The Bessel's, Legendre, Hermite, and Legendre functions are the special functions. These are the figures. These are the functions. This is the functions of Bessel's. This is the Legendre's equations, and this is the Hermite equations. We will draw the figures of these after solving the different differential equations, which are Bessel's, Legendre's, Hermite, and Legendre functions. These are the special functions. So first, what is meant by a special functions? So first, power series solutions of differential equation. Power series solution of differential equation we know that the solutions of a differential equation d2y on dx square minus y equal to 0. The solution for this, let assume y is equal to e to the power of x is equal to, already we know that what is the formula for e to the power of x, 1 plus x divided by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus and so on, or we will take y is equal to e to the power of minus x. This can be written as 1 minus x divided by 1 factorial plus x square by 2 factorial plus minus x cube by 3 factorial plus and so on. These are power series solutions of the solution given differential equation, Another example of the differential equation is example of differential equation is d2 y upon x square plus y equal to 0 is satisfied by power series is satisfied by power series is y is equal to, let's y is equal to sin x, and sin x can be written in the form of x minus x cubed by 3 factorial plus x to the power of 5 divided by 5 factorial minus x to the power of 7 divided by 7 factorial. This idea leads to the methods of obtaining the solution of the linear differential equation. The linear differential equation of second order series form. So these are the example of the power series solutions of a differential equations. Before going to solve the differential equations for the power series of Bessel's, Legouis, Hermite's, we will discuss about what is meant by ordinary point, then we go for singular point, and then regular singular point and irregular singular point. Then the method of Frobenius. Frobenius has given the method how to solve the power series solutions of a differential equations. First, we will discuss ordinary point. What is meant by a ordinary point? So, ordinary point. Consider the equation P naught d2y upon 3x square plus P1 dy by dx plus P2 y is equal to 0. Then we called as a ordinary point of this equation, where P naught, P1 and P2 are polynomial x, x. So x is equal, consider when x is equal to a, x is equal to a is an ordinary point, of the above equation. If P naught does not vanish for x is equal to a, is called singular point. Singular point if P naught vanishes, Thus, for x is equal to a, then x is equal to a is a singular point, a singular point of the above equation. Above equation, others we can carry as equation 1. We write as equation number 1. Equation 1. Okay. The general solutions of this equation, general solution of a linear differential equation, of second order will consist of two series, say y1 and y2. Then the general solution will be the general solution will be y is equal to a y1 plus b y2, where a and b are arbitrary constant, where a and b are arbitrary constant. That two infinite series, for example, the two infinite series, that is y1 and y2, the two infinite series are said to be linearly dependent, dependent means dependent if one is multiple with the other. If one is multiple with the other, or otherwise they are said to be linearly independent. So now we know that what is meant by an ordinary point and singular point. So power series solution at an ordinary point. How do you solve power series at an ordinary point? Power series solution at an ordinary point. A power series solution. Power series solution. The differential equation. Enter equation number 1, where differential equation P naught d2 y upon dx square plus P1 of x dy by dx. So we can write here P1 P naught of x dy by dx plus P2 of x y is equal to 0 at an ordinary point. At an ordinary point at x is equal to. So at x is equal to a, ordinary point means P naught does not vanishes. Then it is called as an ordinary point. And at x is equal to a, if P naught vanishes, then that is called as a singular point. For this equation, P naught of x d2 y by dx square plus P1 of x dy by dx plus P2 x y is equal to 0. An ordinary point at x is equal to a, the solution can be obtained. Solution can be obtained using the following steps. So again, this is a linear differential equations. It is an ordinary, it satisfies the ordinary points. Then how do you solve this equation? There is the following steps will explain how do we solve this series solutions. First, of the differential equation, solution of the differential equation x is equal to 0, instead of a we are taking a 0, is an ordinary point that is when P naught does not vanish, or x equal to 0. So now what would you do? First, the procedure for this one, let us assume y is equal to a naught a1 of x plus a2 x square plus a3 x cube plus and so on an x to the power of n. We will write this is the summation n is equal to 0 to infinity. Then we write ak x to the power of k be the solution of the given differential equation. This is the first step. So now second step will be find dy by dx d2y by dx square etc. So first we will find dy by dx. Now already we know that y is equal to a naught a1x and a2x square. Then we will differentiate this one dy by dx. So we will write here dy by dx can be written as differentiate with this one. We will get a naught will be 0 because the constant term. This is the a1 plus 2 a2 x plus this will be 3 a2 x square plus and so on. We get k ak and then x to the power of k minus 1 plus and so on. If I write this one in summation, we will get x equal to 0 to infinity. Here we get x is equal to 1 to infinity k ak sorry k ax to the power of x to the power of k. Here x is equal to 1 because when you do the differentiation, then constant will be term will be 0. Then again we will do differentiation with respect to x. Then we get d2y by dx square. After differentiation, we will get, and write in the summation form, k is equal to infinity ak then k into k minus 1 x to the power of k minus. Okay. So now the next term will be third step. Substitute the expansion of y dy by dx d2 y upon dx square etc. in the given differential equation. Given differential equation, that is equation number 1. And the fourth step is calculate a0, a1, a2, so on coefficients of various powers of x by equating the coefficients to 0. Okay. Then fifth is substitute the values of a0, a1, a2 on the differential equation. Differential equation that is equation 1 to get the required series solution. Solution. Okay. So now we studied about ordinary point and how to solve the power series solutions of a differential equation at an ordinary points. So we will discuss regarding the singular point and regular singular point, the irregular singular points. Solutions about singular points. Solutions about singular point. There are two types of singular points. There are two types of singular points. One is regular singular point and another one is irregular singular point. First one is regular singular points. Irregular singular points. So we will define first what is meant by regular singular point, then irregular singular points. If they are given differential equations, how do you find whether it is a regular singular point or it is a irregular singular points? Definition: consider the equation y double dash plus p1 of x y dash plus p2 of x y equal to 0. Again, I will cube. This is equation number 1 for the solution about a singular point. So now, and assume that at least one of the functions p1 and p2 is not analytic. Is not analytic. Not analytic means p1 is equal to infinity or p2 is equal to infinity. In this equation, if you take the area differential equation, if p1 is equal to infinity or p2 is equal to infinity, then p1 and p2 are either is not analytic. At x is equal to a, it's a singular point of equation 1. So now we come to know that what is meant by a singular point. Okay, what is meant by a singular point? So for example, in this equation, either p1 or p2 are infinite. If its coming value is infinite, and x is equal to a is a singular point of equation 1. Consider q1 of x is equal to x minus a p1 of x, and q2 is equal to x minus a whole square p2 of x. Okay, if q1 and Q2 are analytic, not infinity, at x is equal to a, then x is equal to a is called a regular singular point. It's called a regular singular point. Otherwise, it is coming a infinity, then that is called as a irregular singular point. Other regular. So now we will solve one or two examples, then we will clearly identify how do we define regular singular point, and irregular singular point. Example, find regular singular points of the differential equation two x square d2y on dx square plus 3x dy by dx plus x square minus 4 divided by 2x square, x square minus 4 here. X square minus 4 y equal to 0. This is equation number 1. We consider this as equation number 1. Okay. So now we will bring this one in the standard form. Already we know that the standard form equation is y double prime plus p1 of x y prime, p2 of x y is equal to 0. To identify the regular singular point or irregular singular point, first we have to find out the value of p1 and p2 and q1 and q2. q1 and q2 convert in the form of p1 of x and p2 of x. So this one here we will divide equation 1 by 2x square. We will get d2y upon dx square plus 3 by 2x dy by dx plus x square minus 4 divided by 2x y equal to 0. Okay. So now if it is comparing the standard equation, we first, what is the value of here p1? p1 is equal to 3 by 2x and p2 is equal to x square minus 4 divided by 2x square, and q1. So how do you find out q1? q1 is equal to, we know that q1 is equal to this is, we have to use this formula, q1 of x is equal to x minus a, q1 of x. q1 is equal to x minus a x minus a p1 of x and q2 is equal to x minus a whole square. This formula we have to use, q2 of x. That is okay, this one q2 of x. Then here I will erase p1 can be written as x into p1. That is because here x is equal to 0, we are taking x into 3 by 2x can be written as 3 by 2. Then q2 is equal to x square p2 using these formulas. Then x square minus 4 divided by 2x square. After simplification, we will get 1 by 2 x square minus 4. Since both p1 and p2 are not analytic. If are not analytic, p1 is equal to infinity and p2 is equal to infinity at x is equal to 0. So first what you have done, x is equal to 0, we are keeping here. In this case, therefore, x is equal to 0 is an singular point of equation 1. Moreover, both q1 and q2 are analytic. Q1 is not equal to infinity. Q2 is not equal to infinity at x is equal to 0 is a regular singular point. Regular singular point of. So now we'll solve one more problem. Example. Find regular singular points the differential equation integration that is x square x minus 2 whole square y prime plus 2 into x minus 2 y dash plus x plus 3 y equal to 0. We have to find the regular singular point of the differential equations. So first this equation we will bring in the standard form, then we will find out the value of P1 and P2. With the P1 and P2, then we are going to find out the value of Q1 and Q2. After obtaining these values, we will come to know that whether it is a regular or irregular singular point. So now solution. So for this first we will divide equation 1 by x square into x minus 2 square divide equation 1 by x square x minus 2 whole square. Okay, then we will get y double prime plus 2 into x minus 2 divided by x square x minus 2 whole square y prime x plus 3 divided by x minus 2 x square. This is x minus 2 whole square y. This is x square y equal to 0. Then can strike out x minus 2 and x minus square root, it cancels. Then here we get P1 value will be 2 into x minus 2 divided by, then I will get x square x minus 2 whole square is equal to 2 divided by x square into x minus 2 and P2 is equal to x plus 3 divided by x square to x minus 2 whole square. P1 and P2 are not analytic. Not analytic means P1 is equal to infinity and P2 is equal to infinity at x is equal to 0. If I put the value of x is equal to 0 here, P1 also come infinity, and now in this P2, if I put the value of x is equal to 0, we get P1 also infinity and P2 also infinity. So, and x is equal, even if I put the value of x is equal to t, we will get the x minus 2 minus 2 is equal to 0. Again, any number divided by 0 will be infinity for P1, and P2 also will get an infinity. So, hence equal to 0 and x is equal to 2. Hence both the points are singular point of 1. Okay, so second, now at x is equal to 0, Q1, you have to know that x minus a into Q1 of x, and Q2 is x minus whole square into Q2 of x. If x is equal to 0, Q1 x into P1 can be written as 2 into x, x minus 2, okay, and Q2 is equal to x square into P2. Because we are taking here x is equal to 0, so x minus a will get x minus 0 will be 0, so that's why we are written x into P1 and x minus a whole square. So here x minus 0 whole square, again it will come x square only, so that's why we are written here x square into, so not here it is P2. X square, this is not minus, this is into P2. This can be written as x plus 3 divided by x minus 2 whole square. Okay, since Q1 is not analytic, Q1 is equal to infinity at x is equal to 0. So x is equal to 0 is an irregular singular point. Irregular singular point. But already we know that the definition of regular and irregular singular point. Then second, at x is equal to 2, again we will put the value of x is equal to 2. Q1 value will be x minus 2 into P1 and written as x minus 2 into 2 into x minus 2 divided by x square, x minus 2 after simplification will be 2 by x square. Okay, then Q2 value, Q2 is equal to x minus 2 whole square P2. This can be written as x minus 2 whole square x plus 3 divided by x square x minus 2 whole square is equal to x plus 3 divided by 2. Since both Q1 and Q2 are analytic, that is Q1 is not equal to infinity, Q2 is not equal to infinity, x is equal to 2, so x is equal to 2 z regular singular point, and is here point. The solution of a differential equation differential equation about a regular singular point can be obtained. So conclusion of this lecture, conclusion of this lecture, we studied about definition of regular ordinary point, and next we studied about singular point. This singular point again we studied regular singular point and regular singular point and irregular singular point. If any differential equation, we can solve the power series solutions of the differential equation. First, we have to find out whether it is an ordinary point or a singular point, or whether it is a regular singular point. So already we discussed about how to solve the power series solution in the ordinary point. The next class we will discuss about solutions of differential equations, the singular point or a regular singular point. This can be solved by using a Frobenius method. Frobenius method. Next class we will discuss about Frobenius method. This method will give the how to solve the series solution, differential equation, okay, by using a Frobenius method. So now I will stop here for this lecture. We will start with the discuss regard Frobenius methods and Bessel's equations of the differential